We're going to have a look at a couple of corner cases that show up when we're executing the tiny machine. In this configuration, the instruction pointer is B. And if we go over to main memory, location B, we'll see that the code for the operator is 4. Now, in the instruction table, decoding 4, we see that the operator is LDA and that it takes an operand. So let's collect the operand from next to the operator in memory, and we see that it's 2. So let's write the instruction in the trace. LDA 2. Now, what does it do? Well, it collects the value stored in location 2, that's 0, and it loads it into the accumulator. So the accumulator actually remains 0. But crucially, because we've just written a 0 to the accumulator, the 0 flag must be set. So let's see what happens. We set the 0 flag, the other flags remain 0, which means the flag register becomes 2. And then we add the size of the instruction, that's 2, to the instruction pointer, and we get D. Let's go round again. From the instruction pointer being D, well, we look at memory location D, and we discover that the code for the operator is, by an outrageous coincidence, also D. Decoding it in the instruction table, we find that D stands for decrement loop index, and it does not have an operand. So we can write that in the trace. Now, what does it do? It decrements the loop index. However, the current value of the loop index is 0. What happens when you take 1 away from 0? Well, we loop all the way around to f, which is also in 2's complement, -1. So the loop index becomes -1. The 0 flag must be cleared because f is not 0. So the flag register goes back to 0, and the instruction pointer goes up by the size of the instruction. That's 1, so we go to E. Now, what's the next thing that happens? Well, given that the instruction pointer is E, let's go to main memory location E and find out what the code is for the operator. It's 3. Let's decode it. Decoding 3, we see it's jump if not 0, and it takes an operand. So let's fetch the operand from just after the operator in memory. The operator is D, so let's write that in the trace. Jump if not 0 to D. Now what does it do? Well, we just cleared the 0 flag in the previous instruction. So that means the condition for jumping is true. The 0 flag is clear. Jump if not 0 to D. We must jump. That sets the instruction pointer to D. Now, let's go round again. What happens next? We look up memory location D. We find the code for the operator, that's D, and decoding it, we find that it's decrement loop index. So we write that in the trace. Now, what does it do? Well, the loop index is currently F, so subtracting 1 from that gives us E, and again we add the size of the instruction to the instruction pointer, that's also E. Because E is not 0, the 0 flag remains clear, and we're done with this instruction. it looks like we're going to be here for a while, because from instruction pointer E, well, we look up in main memory and we see that the opcode is 3, and decoding 3 we get jump if not 0, and it takes an operand, so we fetch that from just after the okay, and the instruction pointer is E, so we go to main memory location E and we see that the opcode is 3, and then decoding the opcode 3 we see it's jump if not 0 with an address operand, and then after the 3 we see that the operand is D, so the instruction is jump if not 0 to D. Now what does that do? Well, we'd better check whether the 0 flag is set, and it's currently clear, which means that we do jump to D, and we're ready for the next instruction. Okay, now the instruction pointer is D, so we go to main memory location D, and we see that the opcode is D. So decoding that in the instruction table, we see we have decrement the loop index. So let's write that in the trace. Now, what does it do? Well, it takes the current value of the loop index, which is 1, and subtracts 1 from it, giving us 0. And then the instruction pointer goes on by the size of the instruction to E. But because the loop index just became 0, then the 0 flag will be set. So let's see how to do that. Halt flag, overflow flag, 0 flag, carry flag. We have 0, 0, 0, 0 here at the moment, but if we make that a 1, we'll end up with the flag register being 2. So the flag register becomes 2. That's the end of the cycle. Let's go round again. We see the instruction pointer is E, so we look in main memory at E, and once again we see that the opcode is 3. Decoding that, we find that the instruction is jump if not 0, which takes an operand, and from memory we can see that the operand is D, so it's jump if not 0 to D. But what does that do? Well, seeing as the 0 flag is actually set this time, then we don't jump. So what we have to do is add 2, the size of the instruction, to the instruction pointer. Now E plus 2 takes us past the end of memory. E plus 1 is F, plus 2 is what? What does the tiny machine do when the instruction pointer runs out of memory? Well, the instruction pointer has only 4 bits, so we only take the lowest 4 bits of the result. And that means the instruction pointer will wrap all the way back round to 0. And that's what happens in this case when the jump doesn't occur. So now the instruction pointer is 0, and we get to see what the instruction is. It's F for flip accumulator. The accumulator is currently, it's been 0 for really quite some time. And we're going then to flip 0, which will give us F, and the instruction pointer will move on to 1. And then we should note that F is not 0, so the 0 flag will be cleared back to 0. And we're ready for the next instruction. We can see from the instruction pointer that we're looking at main memory location 1, where we see that the code is 7, and 7 decodes to put. So what's going to happen? We write put in the trace, and we record that the output was the current value of the accumulator, which is f, and I'll copy it into the output queue, and then we can move on to the next instruction. Put is size 1, so the instruction pointer moves on to 2. And what's in memory location 2? Well, it's instruction number 0, and if we decode that, it's halt. I'll just write that in the trace, and then I think I've run out of board and I haven't eaten for days.